The second video, I'm going to talk about implicit differentiation, what it means to be implicit and explicit, then the procedure behind solving for dy dx, or even like higher derivatives, given a relation between x and y. Then I will go over some examples. And last video I spent like 36 minutes talking about the chain rule and like the f and g tables, and it's very important because we're gonna sort of treat y as a function of x, and you'll see why we use chain rule. So I really honed in the f and g tables that I like to use, and I'll offer that as a hopefully something that you can use to help you with AP Calc. The first thing that I'm going to do is define what it means to be implicit or explicit. So we've always up to now been dealing with explicit functions. They take on the form y equals f of x, like y equals g of x. Here, it's clear what our independent and dependent variables are, but in the case for implicit functions, they will always take on the form f of xy equals 0. This may look confusing, but if you just go back to our analogy for what functions represent, then it won't be too bad. You can spend a couple minutes really understanding the concept of this. So if we have our function f, and we have our input. Now our input's two numbers. It's an ordered pair. And you can think of this as some point xy on a graph. And what this is telling us is that we put in x and y into f, and then we'll get 0. This might look confusing, but I'll give an example. If we have the equation x squared plus y squared equals 9, basically what this is telling us is that for any point x and y, if this is true, this will be in our solution set. So this is telling us that for every x squared plus y squared, it's going to equal 9. So this is the point 3 comma 0. And as you can see, if we square both of these coordinates, so x squared is 3 squared plus 0 squared equals 9, that point will lie on our solution set. And this is a circle because of the Pythagorean theorem. If you remember, like sine squared plus cosine squared is 1, and in this case our radius is 3. But for example, the point 5 comma 0 isn't in our solution set because we get 25 equals 9, which obviously isn't true. And you might be wondering, and you might confuse this with our f of xy, but this isn't really true because remember, it has to be equal to 0. Well, that's really easy. We can just subtract 9 from both sides. And it's sort of like solving for 0. So what set of xy satisfies this equation? It's the same thing here. And then if you notice that then our actual fxy equals x squared plus y squared minus 9, which is 0. So this is an implicit function. So this I'll say is not nearly as important as what I'm going to talk about now. This is just me going over the formal definition of implicit and explicit functions, just in case, it could help you understand why we do the things we do later on. The last prereq knowledge that I'll talk about is what the derivative operator means. Like I said, this is an operator. So is plus, so is minus, so is times, divide, square root, so on. And for example, in the case of plus, we take in two numbers, like 3 and 2. We use the plus operator in the middle, and the plus operator tells us to add them. 3 plus, this doesn't make any sense, this doesn't make any sense, and this doesn't make any sense. Like, there is no interpretation of just 3 plus and plus 2 if we're using this as an operator. So is ddx on its own, right? And what I want you to notice is the dx on the bottom. If we have a graph, right, I'll use a different color. Remember what dx represented. It represented the infinitesimally small change in x, and then later on we'll talk about the change in y. So the change in y and the change in x. The derivative operator is what we've been using to solve the like for example, f of x equals, y equals f of x. And while we didn't really show it, we actually took the derivative of this entire thing. We did it to both sides. All right, and then this becomes dy dx, and this becomes just f prime of x. So while we were just kind of writing f prime of x, it's important to understand we sort of multiply, and it's very iffy, but we kind of treat this as a fraction, right? We're taking the change in something over dx, and in this case it's going to be y. So you can also write this as df dx, the change in f over the change in x. And notice that it's not dy, right? Because we are taking the derivative with respect to x, the horizontal distance. We're taking the derivative with respect to x. I need you to really understand that it's with respect to x. So if you've understood with respect to x, I'll use a different color just to emphasize the difference in variables, then you might see why something like this might be a little bit problematic, because we're dealing with two different variables here. But how we're going to tackle this is we're going to treat y sort of as a function of x, and then this becomes d dx of y of x squared. And if you notice here, this is sort of a composite function. This is exactly a composite function. So if you recall from like last video, our outer function is going to be x squared, and our inner function is going to be y of x. And I'm going to start writing this as just y, because as long as you understand that I'm treating it as a function of x, then we can just shorthand notate it with y. And recalling chain rule from last video, which we spent 35 minutes on, let's just see what we get here. So f prime of x is going to be, by power rule, 2x. And g prime of x, well, what is g prime of x? So I'm going to write it up here. G of x equals y of x. Now we're going to take the derivative with respect to x on both sides. So we get d dx gx equals d dx yx. And this becomes g prime of x, and this becomes y prime of x. But you can also think of it as dg over dx and dy over dx. I'm going to use this because that's what we're going to be solving for later on, but you can also use y prime. That's perfectly valid. But notice here, we're kind of multiplying this, like dg dx, dy dx, because remember this operator, the change in something over the change in x. This is the change in g over the change in x. This is the change in y over the change in x. Let me fill in this table, and let's just see what we get with chain rule. So chain rule says put this into here, 2 times y times g prime dy dx. And this is also just 2y y prime. If you notice here that like this kind of was just our normal power rule for y, because it would be 2y. Well, we also have to tack on this change in y. And that makes sense, right? Because if we're treating y as a function of x, we also have to account for that rate of change in those directions. That's what chain rule has been telling us. Here's where that comes from, right? If you can take the mathematical leap and understand that y is going to be usually our g of x, we're going to plug in the y into f prime of x by chain rule. And then the only difference is we're going to have to account for that change in y with multiplying by g prime of x. So then we can just treat y with our normal derivative rules. For example, like e to the y. Well, the derivative is e to the y, but don't forget the y prime. Alright, after all of that talk, we can actually start to do a problem now. So let's find dy dx if, let's use the problem from before, so like x squared plus y squared equals 3 squared, or this is just 9. Remember, it's going to be a circle with radius 3. And what does dy dx represent? Well, at some point xy, dy dx represents the slope of this tangent line. So m equals dy dx at that point. And what we'll see later is that dy dx is going to be a function of most likely 2 variables. So dy dx equals g of xy. And again, xy, you put it in this function g, and you get some number. Let's just call it c. Well, actually, this is just going to be dy dx. So we're going to have to put in coordinates on this circle, and then we'll get the slope of that tangent line. But we'll do that later. So how we go about this is we have x squared plus y squared equals 9. Let me rewrite that. We're going to take the derivative with respect to x on both sides. We have to do it on both sides because, remember, it has to be equivalent. We're going to split this up into d dx x squared and d dx of y squared. 2x is easy enough, that's just power rule. And I'll do y squared in a sec, but d dx of 9 is a constant, 0. So now let's find y squared, derivative of y squared. We did this earlier, but it's good practice. So our f is going to be x squared, our g is y, our f prime is 2x, and our g prime is dy over dx. Put this into here, 2y, and multiply by this thing, dy dx. So 2 plus 2y dy dx. And then I will go over the steps, all of the steps in more depth later. This is just a proof of, this is just an example. But now I want to solve for dy dx. This is just an algebra problem at this point. I'm going to subtract 2x from both sides. And then I'm going to divide it by 2y. And what you'll see here is I just get negative x over y. So again, dy over dx equals negative x over y. Sorry, negative x over y. And this is a function of 2 variables, so we have to plug in a point. Let's go to our circle. So let's say we plug in this point, which is 0, 3, which lies on our circle of radius 3. So our slope is going to be negative, what's our x coordinate? 0. Our y coordinate is 3. I'm literally just plugging in these values. And this is 0. And this makes sense because this tangent line is completely horizontal at this point. And the same thing for over here, because x will be 0. You can also fact check this with here, this infinitely steep line. This point has coordinates 3, 0. If this is a derivative function, then we get negative our x is 3 or 0. And this is going to cause some infinity problems. So this does make sense. Just remember, you're plugging in 2 numbers here. And usually one of them will be given, like what is the slope at x equals something. But also be careful because there could be multiple y values, right? X equals 2, for example. This is x equals 2. I'll use red because it's getting crowded. Oh, sorry. These are both x equals 2, so you might have to find multiple tangent lines, but the point is you just have to remember to plug in 2 coordinates. So these steps are given to you by Flip Math, I'm pretty sure, but I also added this simplified problem just in case, because, for example, if you have like 5 x squared over cosine y equals 3, I doubt you want to use power rule, so before you do any derivatives, you can multiply both sides by cosine y, and this is much less annoying. But then we go ahead and take the derivative. We're going to separate all the dy over dx terms, usually on the left, and then this is the non-dy dx terms. If there's multiple, like if you have like a of x dy dx plus b of y dy dx, we can factor out the dy dx dependencies, and then we'll divide everything here to solve for dy dx. But that's just an algebra problem. The one thing I will say is you do have to be somewhat good at algebra, obviously, and then your derivative rules, because you cannot risk getting confused because the y is going to be confusing for a lot of people. You just have to be really good at your derivative rules. So I suggest practicing these two if you're having trouble with implicit differentiation. And then 5, plug in xy if necessary. Okay, so finally now we can start doing an example. And my biggest piece of advice is that if something doesn't make sense, always go back to your fundamentals and how you actually derive it. I really like to stress the derivations because I believe that being able to derive your own things is much more important than memorizing them. So, for example, like if you see this, the x plus y doesn't really make a lot of sense, but if you just, for lack of a better word, just hush up and go back to your how we did everything else, then it will fall into place. So I'm going to take the derivative of both sides because I don't really need to simplify it. So let's move this over here. So d dx of sine of x plus y. Clearly this is a composite function, and we can check that later anyway. So my outer function is going to be sine of x, and then my g is going to be x plus y. If I plug in g into f for f of g of x, then this is equivalent. So we know that this is correct. F prime, g prime, this follows standard. And notice that this is just x. There's no real y because it's going to be, I didn't write this before, but this is f of x. So technically g is also just a function of x because this is x plus y of x, right? And it's solely dependent on x. So if you're able to figure that on your own, that's a really good observation. But taking the derivative, we get cosine of x, and here we get 1 plus, remember, dy dx. So now we put this into here. I'll just use an arrow. Cosine of x plus y times g prime. So 1 plus y prime. So we get cosine x plus y times 1 plus y prime equals normal power rule, so just 2. I want to solve for y prime, so I'm going to divide everything by cosine of x plus y. So I get 1 plus y prime equals 2 divided by cosine of x plus y, and then subtract 1 from both sides. So y prime equals 2 over cosine x plus y minus 1. And that's your answer. Here's an example where you might need to use more like the chain rule, like twice in implicit differentiation. So again, I'll start off taking the derivative of both sides with respect to x. The left side is easy enough. This is just 4. And I'll do this in a different color because I already know I'm going to be using multiple f and g tables. So my f is going to be cosine of x. My g is y squared. F prime, g prime. And we've already done y squared, but I'll just do it one last time just to emphasize the differentiating y with respect to x. So x squared, y, again, you can check, put in g into f, you get y squared. We're trying to find g prime. This is 2x, and g prime is going to be dy dx. So g prime is going to be, putting this into this, 2y times, this is y prime, so 2y y prime. So 4 equals, putting this into here, so negative sine of y squared times 2y times y prime. Now, this is easy enough. All we need to do is just, to solve for y prime, divide everything by negative sine y squared over 2y. And I'll do that in white again. Y prime equals 4 divided by 2y sine of y squared. So it's really not that bad. Then you can simplify it to this, because, yeah. This one, take the derivative with respect to x on both sides. Ln y squared plus cosine squared x equals derivative with respect to x of 1 minus y. So here you might realize that this is simplifiable. So this is d dx, and if you recall your natural log rules, so like natural log of x cubed, I bring down the power, so 3 ln x. So this would be 2 natural log y. And if you're confused how I got this, then you're going to have to go back and review some of your algebra, but I can help with that as always. Dx cosine squared x equals this constant 0 minus, and d dx y is just dy dx. Probably the easiest one. So let's use, I'll bring out the 2 here. So we want to find the derivative, and I'll do this in red. So we want to solve derivative with respect to x of ln of y. Again, set up our f and g table. Natural log of x, g is y, f prime, g prime. Again, plug in g into f and it's equivalent, so we know that this is correct. This is 1 over x, and g prime is dy over dx. So this is going to be, put this into here, 1 over y times dy over dx. So we're multiplying by 2 here, so this would be 2 over y dy over dx plus, and I'll do this in blue just for a good practice on the chain rule. So for derivative of cosine squared x with respect to x follows as normal. F is x squared, our inner function is cosine x, f prime g prime, this is 2x, and this is negative sine x. So put this into here, we have 2 times cosine x times negative sine x. So negative 2 sine x cosine x. Put that into here. Equals negative dy dx. And this seems a little bit more confusing, but all you have to remember is we want all the dy dx terms on this side and everything else on the other. So I'm going to start off by having the white terms be dy dx. I'm going to add dy dx here. So plus dy dx. And then I'm going to add 2 sine x cosine x to the other side. And I'll do that in red. So 2 sine x cosine x. Here, I'm going to factor out the dy dx to get 2y, 2 over y plus 1 times, again in white, dy dx equals 2 sine x cosine x. Sorry, it's a bit messy. And then finally, divide everything by 2 over y plus 1. And that's our answer. So it's just about manipulation, factoring out all of the dy dx is probably like the most satisfying part about solving these problems, but it's all algebra. Alright, so this is an example of where I would use like product rule and chain rule at the same time, so I'll go a bit slower here just so we can make sure we don't make any mistakes. So the 6xy term in particular is going to be a little bit problematic here, but no worries. So let's take the derivative as usual of both sides equals derivative of 6xy 3x squared plus, and following the pattern where we can just tack on the y prime. I'm not going to go to the chain rule there because I want the focus to be what we do here. So 6, I'm going to take out the scalar of 6, so derivative of xy. And I'm going to do this in red just so we can see it better. But let's make another f and g table. And here, hopefully you can see we can use the product rule. F is x and g is y. F prime is going to be 1, and g prime is going to be y prime. All red equals. And remember product rule, f prime g plus g prime f. Alright, so we're going to multiply these two things, y plus these two things, x and y prime. So it wasn't actually that bad. And then of course we're going to multiply this by 6 to get this. So in blue, I'll rewrite this entire thing. 3x squared plus 3y squared times y prime equals 6y plus 6xy prime. Like I said before, we want all the derivative terms on the left, and then everything else on the right. So this doesn't have a dy dx term, so I'm going to subtract 3x from both sides. This is a y term, or y prime term, so I'm also going to subtract 6xy prime from both sides. And this will cancel out, and let me rewrite this. So 3y squared times y prime minus 6xy prime, and then I guess I'll write in red, equals 6y, these will cancel out, and then we have minus 3x squared. I kind of skipped steps, but up to now I'm assuming you'll be able to follow along. If not, you can pause and see what I did, or ask me. Here I'm going to factor out all the y primes, so 3y squared minus 6x, and I want to emphasize the y prime here, equals 6y minus 3x squared. And then finally, we're just going to solve for y prime, which is easy enough. We just divide everything by this thing. So 6y minus 3x squared divided by 3y squared minus 6x, and which will equal this thing by factoring out the 3. So this one looks to be another difficult one, and I'll go over this as well. So again, this looks like by inspection a product rule already, and let's start by differentiating both sides with respect to x. So d dx 2y squared, and I'll do this on over here in red. So we want to find d dx. And I'm just writing everything out so we don't get lost. Our f is ln x, our g is e to 3y, and I will clarify this is product rule. So f prime is 1 over x, and g is going to be following the pattern where we can just take the derivative with respect to y first, and then just tack on the y prime. So this is 3e to the 3y, right? Because I just bring down the scalar to the y. Sorry, g prime equals. And then I tack on the y prime. And now I just have to cross multiply because f prime g plus g prime f. So f prime times g is e to 3y divided by x, and then I add on ln x times 3e to the 3y times y prime. So this entire left-hand side is e to the 3y over x plus 3, just bringing out the 3 to the front here. So 3 ln x times e to the 3y times y prime equals, and again, power rule for y, but then also not forgetting the y prime. And this looks a bit messy, so I'm going to put these in parentheses. So I want to move all of my terms involving a y prime to the left, so let's go ahead and do that. This is already here, so 3 natural log of x times e to the 3y times y prime. I'm going to subtract negative 4y times y prime on both sides. So these are two terms. And then on the right side, everything that's not y prime. So I'm going to subtract this term for both sides to get rid of that and move it to here. So negative 3 e to the y, or e to the 3y over x. Now I'm going to factor out the y prime from all of this. So yeah, sorry, it's a bit messy. This is a negative sign. Y prime, 3 natural log of x times e to the 3y minus 4y. If you want to prove to yourself that this is correct, distribute this out, and then you should get the same thing. Equals negative e to the 3y over x. And then simply divide everything by this giant horrible mess. So y prime equals negative e to 3y over x times 1 over, because we're dividing, 3 ln x e to the 3y minus 4y. And that should be your answer. Alright, so this question, I didn't screenshot that part, but it wants us to find the slope of the tangent line at this specific point. This is what I meant by when we find a function, right? So dy over dx, sorry, it's messy, is a function of both x and y. Well, we're going to plug in pi fourths and pi halves in for x and y. So we have like two quote-unquote inputs. So first we need to find the function for dy dx. So like always, differentiating both sides with respect to x. And I will go through like every single step here just because it's one of these questions and I don't want you to get lost. Y cosine 2x at pi over 4. So the first one I'll do in red up here. This looks like another product rule thing. So f and g, f is x and g is sine 2y. Hopefully you can see that because I'm multiplying them together. F prime is 1. To find g prime, again we'll use our f and g tables. I'll use blue. So also to clarify, product rule, chain rule. So sine of x is our outer function, our inner function is 2y. Plug in g into f, and you'll see we get the same thing, so we know it's correct. F prime is cosine x, and g prime is 2 times dy over dx, which hopefully you can see why. I'll just call it y prime. So again, chain rule tells us put this into here and multiply it by this. So I get cosine of 2y times 2y prime, or 2y prime cosine 2y. Then using product rule, we're going to multiply f prime and g. So it's just sine of 2y times 1 plus this times this. So 2xy prime cosine of 2y equals, and then we'll make more space so we can find this derivative. So product rule first. F, I'll use green, I guess. Fg, our f is y, our g is cosine of 2x. F prime is going to be dy over dx, or y prime. G prime is just going to do, I'll do the table, why not, just for good practice. So finding G prime, f G, outer function, chain row here. Outer function is cosine of x, inner function is 2x, f prime is negative sine x, and here it's just x, it's not y, so this is just standard power rule, which is 2. So negative 2 sine of 2x, I got this by multiplying G prime to putting this into here. So now that I've solved for G prime, I can apply product rule here. I'm going to write this all down here. So unfortunately, I will have to rewrite the left side, but no problem. Right, and this is equal to the product rule, which says f prime g, so y prime cosine of 2x, and then plus f prime, or fg prime, so minus y minus 2y sine of 2x. And now we just have to notice all of our terms that involve a y prime. So this term involves a y prime, and this term involves a y prime. This is already on the left, so I'm going to keep it there. So 2xy prime cosine of 2y. And I'm going to subtract this term so that I can move it here. So minus y prime cosine of 2x. By subtracting it means it's not here anymore on this side. I brought it over here. And in white, I'll do the non-terms. So subtracting sine of 2y from both sides to get rid of it on here and to move it over here. I have sine of 2y minus 2y sine of 2x, which was already on the right side. Now I'm going to factor out the y prime. So y prime times whatever is being multiplied by, so 2x cosine 2y minus, that's gone, so cosine of 2x. And again, if you want to prove to yourself this is correct, we'll distribute this out and you should get what's up here. And then this side, I guess I'll just factor out the negative 1, so negative sine 2y minus 2y sine, plus now, sorry, 2x. Now we just have to divide everything by this term, which is going to look really, really ugly, but oh well. So negative sine of 2y plus 2y sine of 2x divided by this entire mess. So cosine 2y minus cosine of 2x. Now remembering that we're plugging this in at pi over 4 comma pi over 2, which is what we want to find the slope at. So this is the point of tangency, right? We want to find the slope. So x equals pi over 4 and y equals pi over 2. So we just plug in pi over 4 for every time we see an x, here and here and here, and then y. So here, here, and here. And this is what you get, and then we'll go through together. So sine, these will cancel, so this is sine of pi plus these will cancel, so pi sine of, this is 1/2 pi, so pi over 2, and then 2, pi halves, because 1/2 pi, cosine of pi minus cosine of pi over 2. Right, sine pi, yeah, that should be correct. And then now we have y prime equals negative, well, sine of pi, if we look at the unit circle, the y value at pi is 0, so 0 plus pi, and then the y value at pi halves, or 90 degrees, is 1, so sine of pi halves is 1, which leaves us with pi, and then this is pi halves times cosine of pi. Cosine of pi is here, so that's negative 1 comma 0, which means this is negative pi over 2 minus cosine of pi halves, the x coordinate is 0 at pi halves, so 0. This is negative pi over 2. And deleting the negatives, because negative 1 over negative 1 is just 1. We have pi divided by pi halves. And I'm going to write this as pi times the reciprocal of this, so 2 over pi. The pi's cancel out, and we get 2. So the slope, or dy dx, evaluated at pi 4, pi 2, at pi over 4, pi over 2 is 2. So here I've taken a screenshot of a Desmos graph of that function, and as you can see, at our point pi over 2, which is here. This is pi over 4, pi over 2. Equation for the tangent line was this, right? So this is our y1, this is our x1, and this was our dy dx, the actual slope of this green tangent line. And clearly, this is tangent. So the last question I'll go over in this video, it's an AP type question, and honestly, these are pretty good for testing your understanding and not just blindly plugging in numbers. So the first thing, obviously, when it comes to these sorts of questions is analyzing what it wants you to look for. So in this case, we want to find f prime of 1. And what you'll notice is that we don't actually care about this side because we only want f prime of 1, which is here. We want to find the slope of the tangent line at this point. And the other thing is, we don't actually know, well, we do, but it doesn't give us the explicit or implicit equation for f of x, so we need to find that out on our own. If you notice this is a semicircle, we can actually just find the equation for the actual total circle, which is x squared plus y squared equals r squared, where r is the radius. Now, the radius here is pretty clearly 2, because it's 2 units away at every single point from the origin. So if r equals 2, then r squared equals 4. So our implicit equation becomes x squared plus y squared equals 4. Okay, noticing that this is actually a function, right? Our vertical line test says that this is a function. So, for example, a circle is not a function because it crosses 2 points with this line. However, a semicircle can be written in terms of y equals f of x. So let's go ahead and do that. So y squared, I'm going to subtract x squared from both sides. We get y squared equals 4 minus x squared, and then I'm going to take the square root of both sides. So y equals the plus or minus square root of 4 minus x squared. So if you notice that we don't actually need to account for the negative because this is half of a circle, right? This circle is the positive version of the square root, and this circle is the negative version. It's positive because all of the y values are above 0 here, and this is negative because all the y values are negative or are below 0, like y equals 0. So we can confidently and rigorously say that y equals the square root of 4 minus x squared. Now finding dy dx is a lot easier because we can just take the derivative of both sides again. So dy dx equals d dx square root, 4 minus x squared. And then this looks like a chain rule problem. F, g, our inner function is 4 minus x squared because that's what we sort of do first. And our outer function, or our parent function, is x to the 1/2. And by power rule, the derivative of this is 1 over 2 root x. And then also by power rule, the derivative of this is negative 2x. So that implies that chain rule implies that we put this into here and then multiply by this. So 1 over 2 times, instead of x, I put in g. So 4 minus x squared times negative 2x. This will cancel. which leaves us with negative x over the square root of 4 minus x squared. Remember, this is dy over dx. And better yet, we can just call this f prime of x, but this is actually only a function of x, and that's a result of us turning this into we converted the implicit equation to an explicit equation. Remember, for implicit functions, we had like dy dx equals f of xy, where we have two inputs. Since we converted it to an explicit equation, we just get y prime equals f prime of x. And as you can see, we only need one variable here. So if you were able to notice that, that's really amazing. But now the last step is we just need to plug in 1. So dy over dx evaluated at x equals 1 equals negative 1, square root of 4 minus 1 squared. This is negative 1 over the square root of 4 minus 1 is 3, so 1 over root 3. Negative 1 over root 3. And let's see if this makes any sense, right? If we had our semicircle and x equals 1 was like here, it should be a negative slope, right? If you just draw the tangent line, and it is. So what answer choice was that? It should be B.